So next we're going to look at the inputs, and starting with the middle part of the diagram, there are three manual buttons. There's a selector switch and two push buttons: a normally open green push button, a normally closed red push button, and a selector switch. Now the common side of each of those switches is tied to 0 volts. And so because we're applying 0 volts to the PLC input when we press the switch, we need to make the common for this bank of inputs connect to 24 volts. So those are the two ways you can wire up an input for a PLC. You can either have common at 0 volts and have the input devices apply 24 volts, or you can have the common wired to 24 volts and have the input devices supply 0 volts. So when the switches are connected this way, that means they're syncing input devices, and the inputs they're connected to are sourcing inputs. The reason we did this is that it was much simpler to make the encoder interface using single transistors that connect to ground when they turn on. And because they connect to ground, we need to tie DC common to 24 volts. And so the switches had to be also connected to 0 volts. In addition, the magnetic reed switches are connected to 0 volts. And then there are two outputs from the RGB controller that signal, they're actually color indicators. So the RGB controller, it's going to distinguish between no Lego, a red Lego, a green Lego, or a blue Lego, and based on that, one of those four colors, it puts out a binary number. We'll talk about that in a little while, but those are also being delivered by transistors that are active low. So because of those electronic components, we made the whole thing active low. Now on the output side, we have the first two outputs connected to the motor control. So the first one is the output that turns the motor on. It's called PWM, and the second output changes the motor's direction. And if you apply a pulse width modulation signal to this PWM control, you can then vary the speed. So we have speed and direction control using these two outputs. The Siemens PLC is able to be configured directly to produce PWM. You can vary the duty cycle, and because the outputs of the Siemens are transistor outputs, they can be switched on and off at high speed. And so we're going to be doing that in the lab, setting up the PWM configuration and allowing us to vary the speed of the motor. Then we have the two pneumatic solenoids that are part of the solenoid valve manifold, one to control the vertical positioner and one to control the gripper. Then there's a control to tell the RGB controller to take a color reading. So when the PLC wants to signal the controller, it just applies a 24 volts to this read pin, and that goes to the color reader. And then the last output here is connected to the conveyor motor. That is also a PWM output, so we can vary the speed of the conveyor. However, you notice there's no ability to change the direction of the conveyor. The conveyor is wired in one direction only. There's no H-bridge interface like there is with the actuator over here. So the conveyor is really only meant to run in one direction. So the bug linear actuator, major components are the 24 volt DC motor, the optical encoder, there's a belt coupling which is inside this enclosure so you can't see it, and that ties the motor to a lead screw which is also not visible. It's inside this cylindrical enclosure. Then there are two magnetic reed switches to be used as limit switches that the PLC uses to detect when the motor is all the way at its retracted position and all the way at its extended position. So the programming is set up so that whenever the extended sensor goes true, the motor is not allowed to go in that direction. And same thing for the reverse direction. And then, of course, there's the actuator arm that moves back and forth from the linear actuator. So this is the schematic for the interface circuit. And the purpose of this is to allow the PLC to control the motor and also to be able to read the outputs of the encoder. So let's start with the motor control first. The two inputs that you see here, DIR and PWM, are 24 volt output, DC output signals coming from the PLC. And those have to drive two inputs on this LMD 18200. Well, the 18200 is not able to accept 24 volts. If you did put 24 volts into the input, it would damage the chip. So we have to reduce the voltage using a voltage divider. So if you wanted to know what the maximum allowable voltage is for the LMD 18200 inputs, you'd have to go and look at a data sheet. So I'm going to pull up the web, a data sheet for the LMD 18200. So I was looking for a okay, and here it is. So if we go down here to the input specifications, electrical characteristics, VIH is V input, well, logic high input voltage, and those are on pins 3, 4, and 5, the ones that we're looking at over here. 3 and 5 are the ones we're concerned with. So it says here they need to be a minimum of 2 volts and a maximum of 12. So they can be all the way up to 12 volts, but obviously 24 is too high. So if we go back to the schematic, you'll see that we've got a 24 volt signal coming in from the PLC, and we're using a voltage divider. So we have 20K in series with 10K. That means that 10K is 1/3 of that total resistance. The total resistance here is 10 plus 20, 30K. So if 10K is 1/3 of the total resistance, it's going to carry 1/3 of the voltage across that circuit. Now keep in mind that this connection to the input is not going to draw any current at all. So it really does not affect the circuit. So this is essentially R1 in series with R3. That's why we can say that the voltage is proportional like that. So 1/3 of 24 volts is 8 volts, which is well under the 12 volt max, and it's also well above the 2 volt minimum to give a high signal, a logic high signal to that. You don't want to go all the way to the minimum, because the lower the voltage is, the more susceptible it is to noise. So when the PLC applies 24 volts to either direction or PWM, 8 volts is applied to one of these inputs. So that's how the PLC is controlling the two inputs. The output goes to the motor, so that just goes straight out to a terminal block, which then gets wired to the motor. So the other components, the capacitors, are there to just reduce the noise from the power supply pin. That 24 volt line is actually coming in from the system, so there's a fair amount of wire delivering that current to the chip, and there's a potential for that long wire to pick up noise. So we put a capacitor close to the chip to reduce the amount of noise at the point where it enters the chip. And then these two components down here, the 2K ohm and the 0.1 microfarad, are actually there to set the current limit on the LMD 18200, so that if it starts to go to too much current, it can automatically shut itself down temporarily to limit the current. Now the components down at the bottom are there to take the signals from the encoder, channels A and B. There's also an index signal from the encoder that happens once per rotation. The A and B signals are actually, depending on the encoder, they might be, I think, 500 pulses per revolution or something like that. Anyway, those are 5-volt signals. They're low current 5-volt signals. So a 5-volt signal is too low of a level to drive the PLC input. So what we're going to do is use the 5 volts to turn a transistor on and off, and the transistor will be connected to the PLC input. Now you might remember from the input diagram that the common of those inputs was connected to 24 volts, which means that the input, in order to be on, just needs to be connected to ground. So that's what the transistor is doing. Every time the encoder pulse goes to a logic high, the transistor turns on and pulls the input to a logic low, which makes it true or on. So in this way, we're taking a 5-volt signal and interfacing it with a 24-volt input. The only two that are being used are channels A and B. The index is not used in the system, but it's there if we ever did want to use it. Now the last component here has to do with the encoder. If you look at the connections to the encoder, there's a 5-volt connection. The encoder is a 5-volt device, so it needs to get 5 volts in order to be powered up. So that connection here comes from a 24-volt to 5-volt DC to DC converter that's been mounted on the board. Actually, you can see it down here in the lower left. And so that means that the board only needs 24 volts, and then the 24 volts gets converted to 5 volts so that the encoder can get 5-volt power. So we have the wires coming to and from the PLC, and another set of wires going to the motor and the encoder. And this is the bottom view of that unit.